So I was asked to tell a story about the use of physical techniques in hydrogenase research, and I would like to speak about nickel iron and iron hydrogenases and how they were studied by physical techniques. But let me start with Gerhard Erdel from the Fritz Haber Institute in Berlin. He said once, real progress in science requires either a new method or a new idea. And he was a physical chemist. He received the Nobel Prize 10, 15 years ago. And it is very clear that he added the discipline of physical chemistry has evolved into a cornerstone of all natural sciences, chiefly through the advent of new methods. So that is certainly true, and let us have a look at the physical methods used in hydrogenase research. There are first of all the structural biology, structural chemistry methods like X-ray diffraction, neutron diffraction, cryo-EM, also NMR, infrared spectroscopy with all its variants, magnetic resonance, I will talk about that today, spectroelectrochemistry detected via infrared, optical techniques, or also EPR, Mössbauer spectroscopy, mainly iron-57, but also nickel-61, as you know, protein film electrochemistry, synchrotron spectroscopies, in particular the nuclear resonance vibrational spectroscopy, H2ase, and so on. And all that is backed up by theoretical calculations on different levels. Density functional theory was very helpful, and also ab initio methods, QMMM, and so on. So there's no way to talk about all that in 30 minutes. So I will focus on the structural methods, on magnetic resonance, and a little bit talk about theory. Let's start with structural methods. What are the problems with X-ray crystallography? You all know that it is difficult to crystallize certain proteins, in particular if you want to crystallize a certain state with a high yield. Crystal quality is a problem. There's limited resolution. Usually you cannot see any hydrogen atoms, which are very important for hydrogenase research. There is radiation damage, in particular in metalloproteins, due to the very intense X-ray beams that are used in modern synchrotrons. There is limited or no time resolution. There are techniques, but in the past it was really difficult to get good time resolution with X-ray crystallography. And high resolution structures at elevated temperatures, at room temperatures, were also not available because the work is now done at low temperatures. So there are alternative methods like the femtosecond time resolved X-ray diffraction using free electron lasers, cryo-electron microscopy, and these two techniques are booming, and I will talk a little bit about that. Nuclear magnetic resonance has not been used, to my knowledge, on hydrogenases, and neutron diffraction, there is a little bit in this field, but not much success came out so far. So first of all, I would like to start with our paper that was done and published in 2015. We managed to crystallize, and not me means Hideaki Ogata and Koji Nishikawa. Here you see a picture of them. They managed to crystallize the nickel iron hydrogenase from De Vulgaris Miyazaki F, and got excellent crystals with very high resolution. In the nickel R state, we checked that there's only nickel R1 in the crystals, and the resolution was certainly much better than 0.9 angstrom, down to 0.89 or even better. Many unique reflections, a good R value. We could detect more than 900 water molecules in the structure, 100 of them inside the protein, very important for certain mechanistic things, and the coordination error was very small. So we got very good bond lengths and also bond angles. And the best that we could see in the nickel arm, maybe the most important part, was that we could see the hydride in the bridge between the nickel and the iron. And the density of this hydrogen was almost twice as large as all the other hydrogens on the average that we saw. And that made quite clear that it's a hydride. And we also saw the proton, which is attached here to the neighboring cysteine. That means we could directly identify the products of the heterolytic splitting of hydrogen at the catalytic center when we prepared this nickel R state. That was important, but there were many other things. For example, the distances. We could see the nickel iron distance comparison with various calculations that were done before the structure came out, showed that this is an excellent agreement. Also, the nickel to hydride distance is certainly much shorter than the one to the iron. So there's an asymmetric bridge. And we could also finally identify very clearly the CO and the CN ligands. We saw hydrogen bonding. We saw a network of hydrogen bonds through the whole thing and many other things. I don't have the time to talk about that. Possible proton transfer channels and so on could be seen in that. There's one point I want to mention because this is I'm coming up later, back to this point, is with this very high and precise structure that we obtained, one could clearly see that the nickel that we saw is in a square planar arrangement. You see all the distances here. This is our structure. And comparison with the DFT structure shows that this is in quite good agreement. And this shows that this is a nickel 2 low spin state. This is important. It's not a high spin state. And this is actually also what we see. And it was an agreement with not only the DFT, also with X2ase data and related other things. So what can be done then with free electron lasers that I've mentioned? In addition to that, you are all aware of this technique, which is around since quite a while, since Neutze proposed that in 2000. It has been shown that this is really working on various enzymes, metalloenzymes, in particular on the oxygen evolving complex in PS2. There are many, many papers on that. The interesting thing is that with this enormous power that is focused on a bunch of small crystals or even no crystals, we get an explosion of the system. But before the system explodes, we get and can measure the diffraction pattern. And that avoids radiation damage. There's no time that the X-rays are damaging the system. It's very fast. It's on the femtosecond time scale. We can explore the time resolution and get structure of short-lived intermediates. So in hydrogenase research, that was not used very much. In particular, it was used only for avoiding radiation damage. The first paper was already published in PNAS in 2014. You see the name of John Peters here, and they could get from the iron-iron hydrogenase of CP1 a resolution of 1.6 angstrom. That was not done. That was done on small crystals on a shifting device that were hit one after the other, and still the result was excellent and good resolution. And they came up with a recent paper, the Arts et al. Paper by King and Peters group, and used this technique to look at structural changes and conformational changes that are usually when you hit with an X-ray in a normal X-ray structure. This is not even, this is 1 angstrom resolution, but still there are effects on these bonds and on these angles and so on, and some damage, which is cannot be avoided. This is not the case with the X-FEL technique with a free electron laser. They get very nice conformational and could then conclude on these important changes. Excellent work. So now, single particle cryo-electron microscopy. There was in the last 10 years actually a revolution in this technique. The Nobel Prize was given in 2017, as you all know, to Frank, Lubitz, and Henderson. The was based on much better sample preparations in vitrified ice on small special grids that they made for making the samples. The electron beam engineers did marvelous things. More sensitive electron detectors were developed, fast data processing, improved software, big data handling, and so on, that all led to this revolution. The advantages are single crystals are not necessary. They showed that atomic resolution can be achieved for the standard apoferritin. They got 1.2 angstrom resolution. For normal proteins, it went down to 1.7, the GABA receptor, for example, which is already very good. And you can see in electron microscopy hydrogens at this resolution, below 1.5 angstrom, they start to show up. This is different from X-ray crystallography because the scattering is different between electrons and X-rays. Then also, I heard a talk by Joachim Frank in Lindau, and he showed nicely that there is something like time-resolved cryo-EM. This is done with rapid freeze quenching on a specialized grid. And so far, they reached something like a few milliseconds. But this can probably be improved, and then you get time-resolved cryo-EM. And the single particle analysis, which is also very important, allows a selection and detection of different states that you can pick out and then make up pictures and movies and so on that. There are still problems. Radiation damage, global and also site-specific radiation damage is hard to avoid. There is a size limitation. It cannot be used for small proteins. The limit is about 50 kilodaltons. Due to sensitivity problems of the system, maybe they can be overcome in the future. And freezing is necessary for cryo-EM, so there are no data at room temperature. So this is a little overview that I put together for you. The first paper I want to mention is the one by Michael Adams. He looked at the bifurcating H2ase and published this year. This is quite recent, and came up with a mechanism for the bifurcation. And we have done almost at the same time. It was difficult to publish this paper by James Birrell and Hideaki Ogata in collaboration with Jamie Blaser in York. The bifurcating iron hydrogenase von Thermotoga maritima at the resolution down to 2.3 angstrom. I don't want to go into the details here because I just noticed that Chipa Chonga, who was involved here, is giving a talk later today on this problem. So I can skip that and have a little bit more time for other things. But this is something. Let's see if I can get this out here for you from the paper. And it also shows structural changes, and it shows a mechanism that we propose. If this is correct, is a thing we have to discuss, in particular with Wolfgang Buckel, who is also here. I see you. Okay, so now the second part that I want to touch upon is magnetic resonance. And there will be a lot of reviewing of the past, but I think it would be important to show that to you again. So there is more or less also a revolution over the last 10 or 20 years that happened in modern EPR spectroscopy. It's not only just the simple X-band CW EPR that we can do. We have now pulse techniques. We can get nanosecond time resolution when we initiate a reaction with a laser. Otherwise, you have to freeze quench, and then you are maybe at a little bit below milliseconds. But all that can be done, and you get EPR spectra also time resolved. We do that with spin echo detection or with Fourier, this free induction decay detected EPR, and sometimes we see a modulation, and that was the reason that the echo envelope modulation technique was developed. In these modulations, these are caused by the interaction of the unpaired electron with magnetic nuclei in the system. So the hyperfine interaction can be directly measured by these techniques, ESEEM or high score. I will come back to that later. This is good for weakly coupled nuclei. To detect all magnetic nuclei, we can do ENDOR, electron nuclear double resonance, the oldest technique already introduced by Fehr in 1956. And there are various pulse techniques. There's also triple resonance and so on. There's electron-electron double resonance, where we can measure spin distances when you have two spins in the system up to 80 angstroms distance. And there is a new and important technique called Aldo-detected NMR, that we can use for measuring large couplings. Okay, so what you usually see when you put your paramagnetic system, you need unpaired electrons, otherwise you cannot do EPR. Your paramagnetic system in a cavity, in a resonator, in the magnetic field, you get a line. This is what we see at a certain magnetic field, and this is characterized by single intensity line widths in particular, and also the G factor. But the G factor is anisotropic. That means if you turn your molecule in the magnetic field, you get slightly different resonance positions due to spin orbit coupling and other effects that are playing a role here. I don't want to go into the details, but what you see is something like that, which is called a powder spectrum. And this powder spectrum has three main G values, Gx, Gy, Gz. These are the principal values. And these are the spectra that we are obtaining in first derivative. And you see many of them later on. This can be measured in the solid state, also when you freeze your hydrogenase in frozen solution. And the best is you have a single crystal. When you have a single crystal and you put it into your magnet, then you can turn the crystal and measure the different planes of your system, and thereby get the complete information about the G tensor. Not only the value, the magnitude, but also the axis orientation. And this is very important. Single crystals. And sorry, I think I'm stuck here. I think I have to go out again and change that. You can also measure that in whole cells. We have done that with C.M. Albrat in the late 90s, and I think nobody took care about that, but I wanted to mention.
Wolfgang, we don't see your slides.
Oh, you don't see it?
Yeah, you're gonna have to share your screen again. Sorry.
Mm-hmm. Good, then I have to go back. Sorry for that. So can you still hear me?
I hear you, yeah, but we can't see anything. So.
Mm-hmm. So I'm back now.
Yeah.
And now I have
with your slide. Yeah.
There we go.
You know?
Yeah, thank you.
Okay, so back to this problem. Single crystals I mentioned, and also that one can measure in whole cells. That is a sensitivity problem in the end. And one can go to higher fields to increase the Zeeman resolution. So there are a few examples from nickel-iron hydrogenase, and then I come to the iron-iron hydrogenase. In the nickel-iron hydrogenase, as you all know, there are three EPR active states, nickel AB, nickel L, and nickel C. And we have measured the spectra, measured the G values for all these spectra, as you have seen, and others have done that too. This is an important thing. And to show, and this was first done by Mura, that this signal is really coming from a nickel complex, we had to label it with nickel 61. And this is showing the spectra. You see nickel 61 has a spin of 3/2. We get back to the laser point of 3/2. We get a splitting into 4 lines. And so we get the whole nickel hyperfine structure from these spectra. And it shows that about 50% of the spin is at the nickel. And that can be also measured with aldo-detected NMR. We also looked at the iron 57 labeled systems to see how much is at the iron 57, and the coupling is really very small. We detected that with high score, and you see a tiny coupling in the range of only 1 megahertz. Here is another important point that I wanted to point out, because this has probably not been realized. The moment you have a single crystal of your system, and you can mount that then and turn it in the magnetic field, and that is something like what you obtain a rotation pattern of your crystal in the EPR spectrum. That can be done over a very large of temperatures. This is room temperature work at 280 Kelvin. And we did that at 10 Kelvin, at 80 Kelvin, just by freezing the crystal in the right way. And you can measure the dynamics. And at room temperature, you can manipulate the crystals. You can you can add gas, or you can do catalytic things with them. Nobody has done that so far. But in principle, this is all possible and should be exploited, I believe. So in this work, we only looked at the G-tensor magnitude and the G-tensor axis, compared that with calculations. These are calculations from Matthias Stein in his thesis. And he clearly could show what the ligand between the nickel and the iron, the third ligand is. OH and OH, both for nickel A and nickel B, a hydride for nickel C, and for nickel L, the position is vacant. This can also then be done with Endor, and that gives additional information. In principle, you can measure each nucleus that is coupled to the electron spin and get the hyperfine information from that. Very important. The most interesting thing is certainly that we detected the hydride already, 19 years ago, in the nickel iron hydrogenase, in the nickel C state. That was worked together with Bärbel Friedrich's group, doing proton Endor, deuterium Endor, when we deuterated it, and also high score. And from all this work, we got the position of the hydride, which is closer to the nickel than to the iron. And this was actually the position coming out also from a calculation that was done in cooperation with Frank Nese's group. Tobias Kramer did that work 10 years later. That was a very large cluster model that we optimized and calculated structural parameters and all kinds of magnetic resonance and other parameters for this system. Hydride in the bridge, and shorter distance to nickel than to the iron. And the distance here is also perfect. Yeah, what Matthias Stein already did in his work, I would just quickly review that. He could show already, more than 20 years ago, the nickel is redox active, iron is not. The EPR shows that the nickel is in a dz squared ground state, or is something missing here. This should be dz squared ground state. Sorry for that this is not working right. The iron is EPR silent. Iron 2 is low spin, not changing the oxidation state due to the CO and CN ligands. This is important to notice. Spin density is delocalized. It is not only at the nickel, but it is also at the bridging sulfur, as you see here. Very interesting. And on some other atoms. The bridging ligand is changing, and single crystal EPR and density function theory identified the bridge, and the nickel SE and nickel R are EPR silent, with nickel 2 in the low spin state S equals 0. Another point that is important to mention is that in EPR, one can also measure the interaction between spins when a spin is sitting, let's say, on the nickel iron center and the neighboring iron 4 sulfur cluster, for example. And this interaction manifests itself in the spectra by a splitting. These are the splitted EPR signals. And the strength of this interaction, this is an exchange interaction between the electrons, Heisenberg exchange, is very important because it is related to the electron transfer kinetics in this case, and can see it easily from the spectra. And another thing, maybe due to the time running, I will very quickly go over that, is that you can also do titrations by poisoning your sample at different redox potentials, and then taking EPR samples and measure on distinct EPR species how they are changing, getting the redox potential. And finally, we did that on the hydrogenase, nickel iron hydrogenase from Aquifax aeolicus, and found out that this can be oxidized and reduced by 1 electron, the distal one, the medial one by 1 electron, but the proximal one can take up 2 electrons and release 2 electrons. So there is a reduced and oxidized in the super oxidized state. And that was quite interesting. And because that explains how the oxygen tolerance of this system came about. You need 4 electrons to put into an attacking oxygen. 1 is coming from the nickel iron center, 1 from the medial 3 iron cluster, and 2 electrons from the proximal one. And that was nicely also seen by other techniques, O17 labeling, by the group in Oxford already some years ago. And the structure of this proximal cluster is very strange. That was seen in X-ray crystallography by the group in Berlin, Bärbel Friedrichs, Oliver Lenz group, and some of the co-workers, and also by Yoshichi Higuchi in Japan. Okay, a few words to the iron-iron hydrogenase. This is the catalytic cycle as we see it, and that we published that last year in a review where James Birrell was the main author. And here, this gives you an overview. Since you have a coupling here between the 2 iron side and the 4 iron 4 sulfur cluster, the unpaired electron can be either be located on the 4 iron 4 sulfur cluster when it is reduced, not oxidized, or it can sit on the iron-iron side. In this state, and in this state and this state, you see the nomenclature here, we get this kind of electronic structure. And for the H-ox and the H-oxCO, we have the unpaired electron mostly situated here on the 2 iron cluster. I also want to mention that Alexei Zilakov measured in iron 57 enriched in the iron 57 enriched system, both H-oxCO and H-ox, all 6 iron 57 hyperfine couplings. And that was then the basis for understanding the J coupling together with Mössbauer spectroscopy and the electronic structure of this coupling of this cluster. Very important for understanding the system that is already published 2007. And this was the system that we had used from that. He also looked at the nitrogen in the ADT ligand before the maturation, the artificial maturation was published in 2009. And we also compared it with a model system, which could be exchanged with N15. And then after this wonderful method was given to us by Gustav and by the group in Bochum, we also labeled with N15 the ADT ligand and also the cyanide, and detected all the hyperfine couplings. That was all correct, that there must be a nitrogen. That's absolutely clear. So what about single crystal work on iron-iron hydrogenase? that was difficult because the crystals were very small, and we had Jason Sidabras in our group, and he worked and set up a resonance structure in which very small samples could be measured. This is the only technical advancement that I show. We have many of these things done by H2ase and Alexei and many others and in our group. This is recently and was done for small crystals. And he looked at PS2 single crystals from Berlin and also from Bochum, from the group, at the iron-iron hydrogenase single crystal from Clostridium pastorianum 1. And this is the rotation pattern. Repeated that in other planes, which is not quite easy. And this gives, for the first time, the location of the G-tensor in the system that you see here. So the last thing I would like to mention is very quickly NMR spectroscopy. Certainly NMR on hydrogenases is difficult to do. The challenges are sensitivity is very low for NMR, requires high concentrations. We work with 1 millimolar or higher. There's high molecular weight, 60 kilodaltons. We want to do all that at room temperature. In aqueous medium, buffer, the lifetime is a problem. The oxygen sensitivity is a problem, making these samples, and it's difficult to create a specific state. So we started with the APO enzymes having only the 4-iron-4-sulfur cluster. In here, this is done 600 megahertz NMR, done with Christoph Fares in the Kohl Research Institute at room temperature. Problem is, I don't have to say that probably to you, that there is a paramagnetic center in the system. Even if you don't see it by EPR directly, there are unpaired electrons there. And this is causing a problem. There could be direct hyperfine interaction, this causes large chemical shifts and causes line broadening in the system. In particular, the contact shift is important, and that depends on the spin density at the iron, on the spin density at the proton you want to look at, on the dihedral angle, on temperature, and so on. But anyway, we managed to see for the APO enzyme, the 4-iron-4-sulfur cluster, oxidized state, reduced state. You see how the lines broaden and shift to larger values. And we also looked at the holo enzyme for HOX and for HOXCO. So this has an enormous potential because you can look easily with normal NMR at various samples and try to get all the hyperfine, all the lines and the chemical shifts. We did that actually on the H2ase state and could show by manipulation of the 2-iron center that there is lines disappearing. This one, when we deuterate the hydride at the iron and the H at the D, and these are the two resonances. This is the H at the nitrogen, and this is the hydride that can be directly measured. So this is a beautiful technique, and we have used that with Constanze Sommer for various purposes, for just analytical purposes, like the selenium labeled system, also the selenium labeled 4-iron-4-sulfur cluster. And you see these are the NMR spectra. So that is possible, one can do that. Here is the 4-iron-4-selenium cluster in the HyDA1 APO enzyme. You see how the lines are shifting, and this has all not been exploited very much, but it is possible. So as I said in the beginning, all this work has been done by various co-workers, and this is a group of people. I hope that I have not forgotten somebody. I'm sorry for all the good work that was done using electrochemistry and infrared spectroscopy and all these things, but there was no time to talk about that today. Also, many cooperation partners. Sorry, I had no nice photo of Jamie. Should get one. And thank you for your attention, and I wish you Merry Christmas.